Perfect. All right, everybody. Hope you had a good lunch. So our next talk will be Shai Ben David. Shai doesn't really need an introduction for this audience. He's one of the towering giants of theory of machine learning. He's worked on all kinds of things, anywhere from learning probability distributions, clustering, domain adaptation, multitask learning, all kinds of things. And today he's going to tell us about something in the foundations of learning probability distributions. Shai is over Zoom, so if you have a question, raise your hand, and then Matus has a microphone. He'll bring it over to you. Shai, please take it away.
Okay, yeah, thank you. So I'm really sorry I cannot be there, and yeah, it would be, I watched some of the talks remotely, and it looked like a great fun. So yeah, I hope I'll be there with some other workshops. Okay, so I just figured that it's not a good idea to spread the virus to all of you. So yeah, what I want to talk about is learning probability distributions, and as I could see from the previous talks, it closely relates both to Nati's talks and to Siva's talks, and even some connection to the last talk by Zico. So let's get started. So there are two themes to this talk. One of them is learning probability distributions, as the title suggests. And the other way is about common tools of generalization theory. So that will be something in the background all the time, that we know that when we usually do theory of generalization, we use uniform convergence and dimensions for capacity control and sample compression and all kind of tools. And we know that in the case of binary label classification, they are all equivalent. But it turns out that in other setups, they are breaking that. This equivalence breaks down. Some of those tools still work, some others don't. So I think Nati alluded to it, and here we will see some concrete examples. So what do I mean by learning a distribution? So it's really a fundamental statistical learning problem. I mean, if you ask what is statistical learning about, you can say you have some unknown probability distribution, say it's the environment, and we get a sample from this distribution, that's our empirical data. And based on this sample, we are trying to learn as much as possible about the sample generating distribution. So that could be described as the general task of what we do in statistical learning. Now, the first two questions to ask is, first of all, what prior knowledge does the learner have when he gets to set up to learning? And the other is, what do you want to learn about distributions? And the most ambitious framework will be, let us assume that the learner starts with no prior knowledge. He makes no assumption about an unknown distribution, just want to do density estimation from samples. And it aims to find what the distribution is. That's basically the task of density estimation. And Siva mentioned it, and it's a very basic task. So namely, we want to come up with reliable, tight estimation of a distribution, say in the total variance sense. So we can show it kind of in a sketch like this. There's some unknown distribution D. It generates an IID sample. This is the input to our program. And our program has to spit out some D hat that should be close to D, say in the L1 distance. So the first observation is that this is just realizing how impossible it is. So let me give you an example. So assume that there is a lottery, and every week you throw 8 10-faced dice are tossed randomly. So you just pick 8 numbers from 1 to 10 randomly, and then you have a ballot, and if you guess all the 8 numbers correctly, you win the lottery. Now assume that I am the lottery manager and I wish to cheat. So here is what I can do. I can toss the set of dice 1,000 times and record the results. And then for the following weeks, instead of tossing a set of dice, fresh set of dice each week, I will just randomly pick the result from my record of 1,000 tosses. Now, this is going to give me a huge advantage because I will just fill 1,000 ballots with those 1,000 results, and I'm going to win every single week. But how long will it take for an observing referee to figure out that I'm cheating? So I'm now sampling from these 1,000 samples, and there was sampled IID from the true distribution. When will the referee detect that there is a cheat here? It's a big cheat. And of course, I mean, it kind of, I think, refers to what Zico was saying, because when you have a generative model, it learned from some distribution, it saw samples from distribution. So say that it only saw the cheated tosses, and it's trying to generate samples that will look like they came from the original distribution. So it is kind of bound to output things that were not among those 1,000 examples. It is kind of another explanation why it is bound to hallucinate. But anyway, that's a side note. And okay, so the claim is that if you have sample sizes, if you want to make it in a formal claim, if you have sample sizes that are independent of the domain size, they cannot distinguish between sample generating distributions that are 0.5 apart in the TV distance. So the total variance distance goes between 0 and 1, being 0.5 apart is as bad as it gets. And why is that the case? Here is the proof. You consider you have a discrete finite domain set of size capital N, and any sample size of size small n, which is less than square root of n, is likely to contain no repetitions. That's the lower bound to the birthday paradox. And the point is that as long as you don't see repetitions, it is equally likely that the samples that you saw were generated by a uniform distribution over the whole domain, or they were generated by a uniform distribution, I would say, half of the domain that contains all those sample points. So there is no way, information theoretically, to distinguish between these two cases, and the total variation between those two distributions is 0.5. So the conclusion is that without prior knowledge, the task of learning what a distribution is, that is density estimation, just cannot be achieved as long as the sample sizes are independent of the domain set size. That's the discrete case that Siva was referring to. Okay, so now it means that there are two major types of problem restrictions that we can address. Since we cannot do the most ambitious everything, one way is to say, assume the generating distribution belongs to some restricted family of distributions. So we can make assumptions in the distribution. We know some prior knowledge about the distribution. It is equal to, say, a mixture of Gaussians, or well approximated by a mixture of Gaussians. That's one direction to go. Restrict our attention to some restricted family of distributions. Another direction to go is to say, I don't try to learn what a distribution is. I'm just trying to discover some limited information about the distribution. So I want to say I don't aim to know what a distribution is, but say I want to predict labels, I want to cluster, a clustering that will fit the distribution, or I want to find the means or higher moments, or any functional estimator. So we split into two types of directions of research. What prior assumptions suffice for learning what the distribution is, and without any prior assumptions, what can we learn about the distribution? So, and what I'm trying to do here is to talk about how to characterize what is possible to do, what is doable in which of those two directions. What is doable with provable guarantees? Okay, so the results that I wish to discuss. So in the first domain, I mean, that's an old result. Maybe some of you heard it already. I want to demonstrate how we can do learning of mixture of Gaussians. And my main point here is to demonstrate the use of a tool of sample compression schemes. And then I want to talk about a more recent result, which is characterizing which families of distributions are learnable. So what prior assumptions suffice in order to guarantee that you can approximate the distribution. And then, if I have time, I will talk about this other direction, which is which properties of distributions are learnable without prior knowledge, or which random variables can be estimated, or functionals, or whatever. And the answer to this is also, it's a result that we got actually in Simon's 5 years ago, I think, that the answer to this question is independent of set theory. Okay, and are some other very strange behaviors of learning distributions. For example, when we learn distributions, realizable is not all you can learn, not all you need. You know, there's a recent paper that says realizable is all you need. It is true for binary classification. For distribution learning, we can show that there are classes that are realizably learning, but once you introduce noise, they become unlearnable. I will not get into that. Okay, so the parallel theme that I want to discuss relates to Nati's talk, and this is what are the common tools of the trade of machine learning theory of generalization. So we have PAC learnability, we have learnability by empirical risk minimization, or in the case of distributions, it will be by maximum likelihood. We have weak learnability, we have uniform convergence, existence of sample compression schemes, finiteness of some dimensions, say VC dimension, and bounded covering numbers. And the nice thing is all of those are equivalent when we talk about binary label classification. So the fundamental theorem of statistical learning is, it's a very clean case. If you have a class H of binary labeled predictors, then all the above are equivalent, and the relevant dimension is the VC dimension, and the equivalence is even quantitatively. We can estimate pretty well the sample sizes if we know covering numbers or VC dimension or sample compression size and so on. So that's a nice case of binary classification. However, what I would like to show is that once we go into the domain of distribution learning, this equivalence breaks down, and many of those are no longer equivalent to each other. So this is the kind of the parallel theme. I want to talk about distribution learning and what can be done, but I also want to talk about, to demonstrate which tools of machine learning generalization are robust to switching from label classification to other tasks. Okay, so the first tool that I want to talk about is the sample compression scheme, and it goes back to the Occam razor. And one way to manifestate Occam razor in machine learning is this sample compression classification prediction. So let me, okay. So what is sample compression for those that don't know? So we have a class of models. In our case of distributions, say that's our assumption that the class is all mixture of Gaussians, and there is an Alice that knows everything. There is a model picks adversarially from this class D, from the class F, and Alice knows what the model is. And now Alice gets some IID samples from this model, from the distribution that we are trying to approximate. And what does the compression mean is that she can send to Bob only a few points from the sample that she got. These few points can depend on her knowledge of the generating model. And we want that Bob, upon seeing just those few points, will be able to recover a distribution which is close to the original one. So that's the general principle of sample compression scheme. Here I was describing it in the context of distribution learning. So I want to compress a sample from a distribution in such a way that upon an advanced agreement, Bob will be able to reconstruct an approximation to the distribution. Okay, and the main insight here, and we say that F has compression of size T if Alice can send at most T points to Bob, and it will suffice to approximate T. Okay, so how it connects to learning? So In the case of binary classification, already Lindstrom and Varmus showed that sample compression scheme for binary classification implies PAC learnability. And 30 years later, Shai Moran and Amir Yudayov showed that the reverse implication also holds. If you have PAC learning, then the class has a small compression size. But this is binary classification. We want to see what is happening when we go to other tasks. So for binary classification, these are equivalent, compression scheme, and the class is learnable. Okay, so in general, one direction works very generally, and this is if you have a class that has sample compression scheme of size t, if Alice can just send t points, then the sample complexity of learning in F up to arrow epsilon is order of t over epsilon squared. So small compression scheme imply sample efficient algorithm. Now, the idea of this proof is very simple. The idea is that Bob just simulates all the possible compressions that Alice could have sent him. If you had initially a sample of size m, there are at most m to the t such possible compressions. And, okay, well, it's running ahead of me. And now we have a small class of representative models, those that are simulated, and we just need the ability to learn from a finite class. And now Bob has a very easy task. He has just m to the t many models to choose from, and he can use a fresh sample and learn from that. That's basically the compression theorem, the direction that says if you have compression, then you can control the sample complexity of learning. So this is this theorem here. If you have compression to size t, you can learn the family of distributions in sample size O of t over epsilon squared, where epsilon is your approximation request. Okay, so let me just demonstrate how we do it for mixture of Gaussians. So I want to show you how we can compress, how Alice can compress mixture of Gaussians. So the simplest case is I have one Gaussian in one dimension. And now Alice gets a set of points of samples. If the sample is big enough, then there will be 2 points in this sample such that the mean of the average between these 2 points is the mean of the Gaussian or close to the mean of the Gaussian. And half the distance between the 2 points is close to the variance. And therefore, these 2 points tell all the story about the single Gaussian. So now we see that one Gaussian in one dimension can be compressed to 2 points. Now, if I have, the nice thing about compression, it's very modular. So now if I have a mixture of k Gaussians, so I can just repeat the same process. So Alice will get a sample from this mixture. For every component of the mixture, she will pick 2 points that tell you what is the mean and what is the variance, and send this k times 2 points to Bob. There is a small, I'm skipping here a small detail. The small detail is, of course, Bob will have to know how to arrange those pairs of points, but we can also send some binary string, short binary string, as long as it's a short binary string that gives a hint. As long as it's a short string, Bob can simulate all of those strings and repeat the same learning process. So if F has compression of size, if the family has compression of size T, the family of K mixtures of F has compression of size KT. Now, similarly, I don't have the slide here, we can go to higher dimension. If I want now, instead of talking about Gaussians in one dimension, if I want to talk about Gaussians in d dimensions, it turns out that I need just 2 points for every entry of the covariance matrix. So I just need order of d square many points in order to compress a Gaussian in d dimensions. And by the same argument, to compress k Gaussians in d dimensions, we just need compression to size kd squared, and we get our theorem that the sample complexity for learning mixtures of k Gaussians in RD is roughly kd square over epsilon square, and it turns out that this is a tight bound. We have a lower bound, which is kind of almost matching. So this improves previous bounds, it's nearly tight, and the compression idea can also be extended to agnostic learning, and we get similar result for agnostic learning of mixture of Gaussians. Okay, so this was a demonstration of a positive learning and a demonstration of the tool of sample compression schemes. So now we saw one example of where you cannot learn if you don't know anything about distributions, like the lottery case. And we saw one example in which you can learn. So now the question is, I mean, there are two questions. One of them is, can this be done efficiently, which I don't know the answer to. But the other question is, can we characterize which families are learnable and which are not? Because we saw mixture of K Gaussians in RD is learnable. We can control the sample compression. Lottery is not learnable. Can we give a characterization of which families of distributions, what prior assumptions suffice for learning? So this is the task that we were set to focus on. Find a dimension or some characterization that characterizes the learnability of mixture of distributions. So just to remind you, this is really a hallmark of machine learning, finding combinatorial characterization of learnability. We know that for binary classification, we have the VC dimension. For online binary classification, we have the Littlestone dimension. For real-valued functions, we have fat shattering dimension. We have for multi-class learning, we have natural dimension, graph dimension, DS dimension. For robust learning, we have a characterization. For private learning, almost for everything, we have a dimension that characterizes learnability. Can we do the same for other tasks for which we don't have such a characterization?
Shai?
So here are a few tasks for which we do not have a dimension.
Shai?
So one of them, as I already mentioned, is learning families of probability distributions. Another one is binary classification with respect to restricted family of distributions. So Nati, I think, also already mentioned it. When we do the PAC characterization with VC dimension, it is characterizes learnability of a class with respect to the worst case distribution. We make no assumptions about the underlying distribution. But what if we know something about the underlying distribution? So now we have a pair. We have a family of distributions, and we have a hypothesis class, and we want to ask, is this hypothesis class learnable with respect to this restricted family of distributions? So that also, we don't have a dimension. This question was asked already by Dudley and Benedek Itai in the early 90s and remained open until now. So here is another setup in which we don't have a characterizing dimension. Another setup is real-valued functions. So we know that we have the fat shattering dimension that characterizes for every epsilon, you can check whether your family of real-valued function is learnable to this epsilon. But can we give a learnability, a PAC-style learnability that will give you a sample size for every epsilon and delta? Okay, so all of those are still problems in machine learning for which we do not have a characterizing dimension. So with the work with Tosca, we showed that there can be no dimension that characterizes learnability for any of those tasks. So there can be no dimension that characterizes learnability of families of distributions. There can be no dimension that characterizes learnability with respect to restricted data generating distributions, and same for PAC learnability of real-valued functions. So I want to turn now to talk a little bit about this kind of result of there can exist no combinatorial dimension. And of course, the first question you should ask at this point is, if I want to show that something does not exist, I need to define it. I need a kind of a high-level definition of a dimension. What is the notion of dimension? So we need a clear definition of what is a dimension that characterizes learnability. And we want a definition which is kind of high level that will capture all those setups of learning. So we consider two common types of characterizations of learning. So one of them is a quantitative notion. So what does it mean, quantitative notion? It reflects the sample complexity of a learning task. We know that the VC dimension characterizes the learning rates of a part of these classes. It gives you, if you know the VC dimension of the class, you know for every epsilon delta, how many samples will you need in the worst case for epsilon delta learning the class. So this is a dimension that gives us control over the learning rates, over the sample size. But the dimension also plays a slightly different role, and this is a qualitative notion. It distinguishes between learnable and non-learnable class. We say that a class is learnable if and only if its VC dimension is finite. So we will give two definitions or high-level definitions of what a dimension is. One will be for what do we mean by a quantitative dimension, and the other, what do we mean by a qualitative dimension. So for a quantitative dimension, so we want a mapping from the family of classes of models to the natural numbers or maybe infinity. And we want to have the following property, that if you have a class of models that it is Spark learnable if and only if its dimension is finite. But furthermore, we want to control the sample sizes. So we want that there is a function that takes the dimension and takes epsilon and delta and tells you how many samples you will need. So if you, I don't know if you see my, can you see my cursor? So, I want to look at it again. You see, so the sample complexity of learning the class Q to approximation epsilon with probability of failure no bigger than delta is bounded by this function f that takes into account only the dimension of Q, and epsilon and delta. So, in other words, such a dimension controls the sample sizes. It kind of says that all the information about the class that you need in order to determine an upper bound to the sample sizes is captured by the parameter d of q. So if I want to know how many samples I will need, I don't need anything else about the distribution. If you just give me its dimension. That's the quantitative result. And we can show that you want to know that you don't need anything else above the dimension in order to tell the sample sizes. And we know that the VC dimension exactly does it for binary classification. And okay, so I'll skip for now the qualitative dimension, and I will talk about the quantitative and then get back to it. So all the dimensions that we know so far, they satisfy the requirements. They all give you sample sizes or mistake bounds or whatever for learning. And we want to show that no such dimension can characterize learnability of classes of probability distribution. So that's the result with my student, Tosca Lechner. So let me give you a high-level description of the idea. So we want to show that there can be no dimension such that once you know the dimension of the class, you can figure out how many samples you need for every epsilon delta. And this is in particular now applying to learning distributions. And the idea is that the learnability of distributions is too rich to be captured by a mapping to natural numbers. The mapping to natural numbers is not rich enough to express all the possible behaviors or even to upper bound all the possible behaviors of learning rates of classes of distributions. So there can be no such function that will upper bound for any class the learning rates. And to prove this result, I need to use a tool from set theory. So the tool that I'm going to use is a notion of cofinality. So let me just explain this tool. So I have two subsets of an ordered set. And I said that A is cofinal in B if for every element in B, there is an element of A which is above it. So A is cofinal in B if for every element of B, I can find an element in A above it. So for example, it's very clear that we have transitivity. If A is cofinal in B and B cofinal in C, then A is cofinal in C, because above every element of C, I have an element of B, and above every element of B, I have an element of A. So let us see some examples. So the set of prime numbers is cofinal in the set of natural numbers. For every natural number, I have a prime above it. If I have a finite set, of course, the cofinality is 1 because the top element is already cofinal in the finite set. If I have the set of natural numbers in the reals, you will see that the set of natural numbers is cofinal in the reals because every real has a natural number above it. And if we now use the transitivity, we get that the set of prime numbers, prime natural numbers, is cofinal in the reals. So the cofinality of an ordering is the cardinality of the minimum cofinal set in this ordering, right? So cofinality of the reals is countable, although the reals are not countable. So do we have any sets which have uncountable cofinality? So if we look at the set of all functions from natural numbers to natural numbers, or even the set of all functions from natural numbers to 0, 1, and we have to define an order. So we order them by eventual dominance. So we say that f is bigger than g if from some point on f of x is above g of x. So that's a natural ordering on the set of all functions. And for this, it's easy to see that no countable set is cofinal in this x, which is all functions from n to n. Okay, so how is it relevant, this notion of cofinality? So the functions from natural numbers to natural numbers do not have countable cofinality. The reals do have countable cofinality. Okay, so what we want is to connect it to this potential notion of dimension. So what I claim is that if I do have a dimension, if D is a dimension, so D goes from the class of distributions to the natural numbers, maybe union infinity, and it's a quantitative dimension, so there is a function such that f of D of Q bounds the learning rate of Q. Then if I look at this family here, the set of all f of D and take epsilon to be 1 over k and delta to be fixed 0.1, then this is a countable family because I have only countably many values of dimension and only countably many 1 over k values for epsilon. And it is cofinal in the set of all rates of learning because our assumption is that f of these f's are above any other learning rate. So if I have such a class, then this countable class is cofinal in the set of all distributions. So now, working towards a contradiction, we will show that the former is a countable set, but the set of all learning rates does not have countable cofinality. So that's a notion of richness, that the set of all learning rates of families of distribution has uncountable cofinality, cannot be cofinal with a countable set, and that will mean that I cannot have a dimension that controls the learning rates. So, I mean, that's the basic idea. So we have a lemma that says that the set of all learning rates when epsilon belongs to 0, 1, and delta is fixed to 0.1, is cofinal in the set of all functions from natural numbers to natural numbers. That will tell us that there is no quantitative dimension that can control learning rates. I mean, it's a good point. I mean, I can give you an idea of how do we construct it. So the idea is that, but I think that's more technical. It's not so important. But the point is that we can construct families of distributions such that they have a big weight on one point, delta 0, and the rest of the weight is on something which is not learnable. Say all finite subsets of the natural numbers, a union of them. So that's a family of distributions. For every subset of natural numbers, I have a distribution which is uniform there with probability 1 over k, and with weight, the rest of the weight is on one point. And the learning rate of such a family of distribution is very high, because if you want to learn just to epsilon equals anything bigger than 1 minus than 1 over k, then you can just use the fixed point. But if you want to get better learning, then you run into the area where we cannot control the learning rates. It's unlearnable. So we can construct from such components a family of distributions which is cofinal in all functions from n to n. Okay, so are there any questions here? So I had a definition of what is a quantitative notion of dimension, that it controls learning rates. Once you know it, you know the learning rates. And I use the tool of cofinality to show that you cannot have such a dimension for learning distributions. Yes.
We have questions? Shai, can you hear me? I have one.
Yeah.
Okay. And my volume is okay? You can hear my voice? Yeah. Yeah, there is another way you could have done learnability of distributions by reduction, where you take the GAN approach, where your task is now to learn a push-forward mapping from some sampleable distribution. And then you just inherit, for the task of learning distributions, all the complexity measures from the complexity measures of learning the real valued mapping, which is the push-forward. So have you considered this, and how does it compare to?
I don't see, I mean, if you go back to the negative example, I mean, you can see that, I mean, if you have a discrete distribution, I don't care what sophisticated GAN you're going to use, you will not be able to approximate it to better than a half in the total variance.
Oh, I'm not giving a sophisticated gun. I'm giving the dumbest possible gun. Also, for me, your half looked like a no free lunch theorem, but the gun I'm suggesting is really just to have a sampleable distribution and then map it through some functions. So the class of functions we can learn are the ones that have a bounded complexity push forward map. We can take it offline, but it does work.
You're giving me a class of learnable distributions, but it doesn't give me characterization that tells me what is learnable and what is not learnable. What you're suggesting is here is another class of learnable distributions. But I want a criteria that will tell me, given a family of distributions, is it learnable or not?
Okay. Are there any other questions? Shai, maybe we can wait just for a couple of seconds since you covered a lot of material. Does anyone have any question about the other parts? Sample compression schemes? Sample compression for mixtures of Gaussians? Shai, everybody in here has an IQ of infinity and understood everything you said. So, okay.
Okay.
Hi, Shai. Actually, it's a question about sample compression. I just didn't fully follow what the meaning of T was. What does the sample compression, that value mean for the family? Because does that mean that for every distribution in the family, there is a compression T that allows the other person to identify exactly or identify approximately? It wasn't clear to me what was meant here.
I was not right. So there are few parameters there. So first of all, there is a parameter that the compression kicks in if the sample is large enough. If you saw, even if I try to compress a single Gaussian, I need enough points to make sure that with high probability, I have in the sample 2 points that approximate the mean. So it kicks in only on big enough samples. And then how many I need to compress really also depends on the accuracy that I want to get. Because there was another hidden component there. If I do mixture, I also need to compress the weights of the different components. So in order to compress the weights, I discretize the interval 0 to 1, and I give you every weight just approximately. And that's another kind of hint that I pass to the learner. So the sample, how big is the compression, depends also on what kind of approximation will it guarantee in the decompression. So there are several parameters there, but it all works into this machinery of if you have compression of size t, then you can learn with t over epsilon square examples.
Can I make an attempt to like make what you just said more precise? So you're saying for this class of distributions, there exists a fixed number t, so that for every accuracy epsilon, there exists an m, a number of samples you need, and a b, a number of additional bits you can send, so that you can compress using m samples, using t of the m samples and an additional b bits to within accuracy epsilon with high probability.
Almost. You just switch two quantifiers.
Okay,
the
so could you...
compression size depends on the approximation epsilon.
So the compression size also depends, so the t also depends on epsilon?
The t also depends on epsilon. It will come in a very weak way in the hint vector, because in the hint, I want to tell you the weights. And the question is how many bits I need in order to give you k weights.
Okay, but that was like an additional parameter b for a number of bits that you need to send.
Right. And the size of b depends on epsilon, and the rest does not depend on epsilon, right?
But so the t, the number of samples that you pick out of the m, doesn't depend on epsilon.
Yes, yes.
Okay, I think that's actually what I said, but...
Yeah, no, it's fine. I'm not blaming you for not understanding.
Shai, we have more questions, just a sec.
About the compression part, I wanted to ask, is Alice allowed to send numbers as well as the samples? And if that is the case, why wouldn't she just send the sufficient statistic up to accuracy?
Right, but the trick is, basically, if you look at the proof that compression implies learning, you just see that we need that the number of potential messages that Alice can send should be just polynomial in the sample size. Because that's how Bob will recover it. So if you're trying to tell too much about the distribution, then it will not be polynomial in the sample that you're given.
Right. Thanks.
All right, Shai, seems good.
Okay, so let me continue. So what I showed is with this cofinality argument, I showed you that the behaviors of learning rates of distributions are too rich to be captured by a dimension. And notice that it also rules out, you can ask, oh, you were asking the dimension to be a natural number, but what if I allow the dimension to be a real number? It will not help us, because if we want that higher dimension makes it harder to learn, then we are playing with the order of the reals, which also just have countable cofinality. So even if I allow dimensions to be real numbers, I will not be able to characterize any learnable family of distributions by a real number that will control the learning rates. Okay, so that was for the quantitative. What about qualitative dimension? What do we mean by a dimension that allows us to distinguish between learnable classes to non-learnable classes? So again, what I have in mind is the visit dimension. So what is the visit dimension? If we want to distinguish between learnable classes and not, we have a countable set of properties. Here, this W, alpha D could be the statement H shatters a set of size D. Now, a class is not learnable if and only if it satisfies all of these formulas. So in the case of visit dimension, a class is not learnable if and only if for every D it shatters a set of size D. Now, on top of it, so we have here a family of properties that you are unlearnable if and only if you satisfy all of them. On top of it, we have one more requirement, is that satisfying such a property, for every such property alpha D and every family of class Q that satisfies it, I can find a finite subclass that demonstrates the hardness. I can find a finite subclass that says every class that contains this core is going to be alpha D hard. So if you go back to visit dimension, if I want you to show you the class shattered a set of size D, then I can give you the 2 to the D functions that do the shattering. It's a finite subset of the class. And every other class that will have these 2 to the D many functions will also shatter D points. So whenever you are alpha D hard, you have a finite evidence, which is a finite subset of the class, such that any other class, if it contains this hard core, will also be alpha D hard. So this is our definition of what is a qualitative dimension that comes to distinguish between learnable and not learnable. And again, every example of dimension that we've seen so far in the literature satisfies this requirement, as well as some candidate dimensions for the problem for which we did not have a dimension so far. So, yeah, so it's a countable family of requirements that just say alpha D hard, and if you are hard for every D, you are not learnable. Okay, so we can think of alpha D as saying D, Q shatters a set of size D. So let me say something about showing how do we show that there is no qualitative dimension either for those families. So I'm skipping here the proof that I just did on the quantitative dimension with the cofinality. Right, so now we want to show that there is no qualitative dimension. And this is also a very general construction. I mean, both constructions, both proofs of non-existence of dimensions apply not only to learning distributions, but also to the other setups that for which we did not have a dimension before. So we say that, how do we prove it? So we are going to need 2 properties from the learning task. One property is that every finite union of learnable classes is still learnable. So that's a property that we have all over the place. If you take a finite union of learnable classes of distributions, then this union will be learnable. If you take a finite union of learnable classes of any task, it will still be learnable. The other property is a bit more tedious. We want that there is some class Q0, and we have a sequence, and Q0 is learnable, and we have a sequence of non-learnable classes that can be arbitrarily well approximated by Q. So you have a Q0, which is learnable. Then you have a sequence of non-learnable classes, such that for every epsilon, one of them is epsilon approximated by Q. And once we have these 2 requirements, we can show that there can be no finite array characterization of this learning task. So there is no finite array characterization for distribution learning once it satisfies those 3 properties. So I can say very little about the proof. The proof basically is saying that if you have this finite characterization, each of those QKs are not learnable. Each of them has a finite core that shows the hardness. Then we can take the union of all these finite cores, and it can be learnable because it's approximated by Q0. That's basically the idea. So there is kind of a general property of a learning task, the existence of such classes, that guarantees that you cannot even characterize it with a qualitative dimension. And I will not get into the proof of how we construct it. I just want to say that this demonstrates that some learning tasks are fundamentally different than binary classification. And in particular, all the classes that I listed cannot be characterized by a combinatorial or finite dimension, even with respect to sample sizes or the question of learnability or not. And one caveat that we have to pay attention to is that we here ask for characterization of pack learnability, that for every epsilon delta, you will be able to get the rate or know it's learnable or not. There is a notion of scale-sensitive dimension, which is a different dimension for every epsilon. When we talk about the fat shattering in our old 97 paper, that was a scale-sensitive dimension for learning the real-valued functions. For every epsilon, you had a different dimension. And we don't know the answer about scale-sensitive dimensions. The proofs that I showed here just show you that cannot have characterization which is scale invariant, like the VC dimension for those problems. Okay, so this finishes my, you remember, we started with saying we want to learn distributions. We cannot learn everything without prior assumptions. I asked which prior assumptions suffice for learning, and I showed you that we cannot characterize it. Now I want to go in the other direction. The other direction is asking which properties of a distribution can be learned. That's very similar to what Siva was discussing in his talk. You want to learn some functional of a distribution without making assumptions about what the distribution is. I mean, the main tool that used by a first approximated distribution, then estimate your functional from the approximation of distribution, we know that will not work because we cannot estimate arbitrary distributions. Okay, so I want to look at this issue of learning to answer queries. So without any assumptions about an unknown distribution, what can we tell about the distribution? So this is a general learning approach, and you have a collection of real-valued functions, or you want to call them queries, or random variables, or functionals, and you get an input, an IID sample from an unknown distribution, and you want to output an estimate of those queries. Now, notice the difference between what I'm telling here and what Siva was talking about. He was talking about estimating a single functional. Here I'm talking about estimating a family of functionals. You want to be able to give an approximately good answer to each of the functionals in this family. So if we want to estimate the expectation of every H in our family or every functional, then it's well understood that's uniform convergence, and it is controlled by VC dimension, but of this family of functionals. But we want to look at a different problem, a weaker formulation, an easier problem, which has lots of applications. So this is what we call expectation maximization. And this is exactly what Nati referred to as Vapnik general statistical learning. And this is a setup in which uniform convergence fails, but you can still learn. So what do we have here? We have a collection of real-valued functions or queries or random variables over some domain X. we get a sample, which is IID by some unknown distribution over X. And you don't want to estimate each of those functionals. You just want to find one random variable that has as high as possible expectation with respect to the unknown distribution. So rather than estimating all of them, we just want to find one which is close to the highest expectation. And that's a very relevant problem to many issues in machine learning. So, for example, if you want to do binary classification prediction, you have a class H, your functionals are going to be the expected error of each of the H's in H. So I don't necessarily need to know what is the error of each function in my class. All I need is to find one function that minimizes the best approximation error. Or multi-class prediction, same thing. Or I want to do case center clustering problems. So you have unknown distribution, you want to find the best case centers with respect to some loss, say quantization or case center or whatever loss you have. So it's not that we need to find an estimate of the cost of every k-tuple of points. We just want to be able to output a k-tuple of points that has close to the best value with respect to the unknown distribution. Same with linear regression. I just want to find a linear function that does as good as possible task. So this expectation maximization problem captures many, many issues. So it's a very high level problem of machine learning. That was Vapnik's general model of learning. And in the context of what we're talking about, Vapnik already asked, can we characterize it? And he didn't know the answer. And we can look at a simple case of it. The simple case is you have some domain X and H is a collection of subsets. Now you have an unknown distribution over X, and you want to find a subset that has as high probability of being hit by unknown P as possible. So you see, I have a distribution, say, over the real line, and I want to find a subset that has as large as possible probability of being hit. So now, let me go back to the tools of the trade of machine learning generalization and see how they break down, some of them break down in this problem. So we talked about all of those tools, and all of those that the PAC learnability is, in this context, is equivalent to weak learnability. It's equivalent to existence of sample compression scheme, but it is not equivalent to uniform convergence. So if we look at this general problem of learning, the equivalence of all of those tools break down. And let me demonstrate it very easily. So if H is a set of all subsets of some infinite domain, and you have an unknown distribution, you get a sample, and you want to give me a set that maximizes the probability of being hit. What set will you give me? You have all subsets of the unit interval. You have an unknown distribution over the unit interval. You need to output a set that has as high as possible chance of being hit. What will you output?
The whole set.
The whole set. So it's very easy to solve it. But we don't have uniform convergence because this collection has infinite VC dimension. We cannot estimate the probability of each of them. So uniform convergence fails and the Emacs learnability holds. It's an easier task than uniform convergence. If you want to learn, Nati already mentioned it, you don't need uniform convergence. In some situations, you can do more easily than uniform convergence. But can we characterize this Emacs learnability? So we want to characterize which classes of random variables or each classes of subsets are Emacs learnable, and can we have a purely combinatorial characterization? So what we are going to do here, this is based on work with Rubes and Moran and Amir Yudayov, and that we did 5 years ago. And the first step that, and Amir Shpilka, and the first step that we took here is that we found a compression scheme for this problem. So as you can see here, you see what I'm saying is even in this general problem, Park learnability is still equivalent to the existence of a small compression scheme and is still equivalent to weak learnability. Of course, the compression scheme here will have to be different than the compression scheme that we used for binary classification because it's a different problem. So what is the compression scheme here? The compression scheme here, if I want to find a set of high probability of being hit, then you get a sample and Alice needs to compress the sample and Bob has to be able to come up with a member of the family that contains all the members of the sample. So let me describe it again. What the monotone compression, it boils down to the following game. Alice gets a finite subset S, and it picks a small subset S prime. S was generated by some unknown probability distribution. It sends it to Bob. And Bob wants to be able to recover some finite set. Say that our family is the family of all finite subsets of our domain. So Bob gets T points. He needs to find a finite subset such that this finite subset is a superset of S. So this is a very difficult game. Think of it again. We have the collection of all finite subsets of some domain X. There is unknown distribution, but the compression doesn't talk about distribution. Alice gets a sample, has to compress it, give it to Bob, and Bob has to come up with a finite set that contains all of the sample. Now, can Alice send to Bob just a bounded size? And note that it depends on the cardinality of X. If X is finite, what will Bob send back? He will send back all of X. It's a finite set. It contains all the sample points. If X is countable, it's also easy. If X is the natural numbers, Alice gets a finite subset of the natural numbers. She needs to send Bob just a few members of this finite set, and Bob needs to come up with a finite set that contains all the sample. What could Alice send to Bob? Again, you have the natural numbers. Alice got a finite subset of natural numbers. And
I'm next to the microphone, so I get to answer the questions.
Okay.
She would send the largest one,
Right.
and then Bob would send all the numbers up to that point.
Right. I mean, we have a very good student here. Yeah. I mean, if you ever look for a supervisor, I will be happy to accept you. Okay, so yeah. So for natural numbers, it's easy. But it gets more interesting when X is uncountable. What will you do in the real numbers? This is much more difficult. You get a finite set of real numbers, say the unit interval. And Alice has to compress it to just a bounded number of points from her sample, and Bob had to come up with a finite subset of the unit interval that covers everything that Alice saw. So it turns out that this gets into infinite set theory. This game you can compress to size k if and only if the domain set is of size at most aleph k. I mean, we saw that if the domain says is of size aleph 0, countable, we can compress to 1 point. But now it generalizes to arbitrary cardinals. Aleph k is the case, so just recall, alephs are the infinite cardinals, aleph 0 is the countable set, aleph n plus 1 is the first cardinality larger than aleph n, and Cantor's theorem tells us that the real numbers are not aleph 0, but we don't know anything else. Cohen's proved that you cannot prove anything else. But if we go back to what we have here, you see you can play this game with k points only if your domain has size at most aleph k. So if we ask, can you play this game over the real unit interval? Can you have a compression over the unit interval? It depends on which aleph k is the cardinality of the reals. And that's independent of set theory. So the question if compression scheme, existence compression scheme for the real unit interval is independent of set theory. So, I mean, I will not get into the proof here why this compression game is equivalent to the cardinality of the set you are playing over. But the conclusion is that the following are equivalent. You are learnable in this Emacs learnability if and only if there is a bounded size compression. So the set of finite subsets of the reals is learnable. You see, your variables are finite subsets of the reals. There is an unknown distribution, and you need to give me a finite subset that approximate up to 1/3 the heaviest set. If it's a uniform distribution over the interval, any set will do because every finite set is 0. But if my distribution is over a finite subdomain of the unit interval, you just got a sample of it. You want to give me a set that captures 2/3 of the weight. It turns out that whether you can do it or not is independent of set theory. So the conclusion is, I mean, this we can do it quantitatively. The sample size is controlled by the compression scheme, which is controlled by the size of the continuum. So the corollary is the class of finite subset of the reals is learnable if and only if the reals are less than aleph omega. Aleph omega is the limit of all the aleph k's, and this is independent of set theory. And this also implies that there is no combinatorial dimension. I will not get much into it, but the point is that when we do in set theory independence results, we construct different models of mathematics that differ in the size of the continuum. So in those different models of mathematics, in one of them, the class will be learnable, and in another, the class will not be learnable. But the point is that we can carefully construct those different models in such a way that if you have a combinatorial dimension, it will not change between the model. So if there was a dimension for Vapnik's general learnability, learnability will not change between different models of set theory. And therefore, here we use the completely different approach to show that no dimension exists for the problem of Emacs learnability or Vapnik's general statistical learning. So I think that I will stop here and take some questions.
I have a question, perhaps the most like a natural question in some sense. Like, yes, it's independent, but that means I can take the reals to be, I think like aleph 1 is the smallest I can take. And in that case, the theorem implies that I can play this game with like 1 point or something.
2 points, with 2 points.
2 points. Yeah. So like, how do I play this game then in this case?
How do you play the game in 2 points? Right, what's the proof there? Yeah, it takes a bit of combinatorial, infinite combinatorics to do it, but I need to have a well-ordering of the reals of type omega 1, which means a ordering of the reals such that every initial segment is countable. You see, the natural numbers are countable, but every initial segment is finite. We can take it one step higher. Order the reals, if the reals are just aleph 1, such that every initial segment would be countable. And then when Alice gets her sample, she picks the top points in this ordering, which is one compression. And now under this point, it's countable. So now you play the game on a countable set, and you need just one another point.
Okay.
It's
thanks.
very non-constructive, but also, yeah.
Shai, just to be clear, you used Zorn's lemma, right?
I use the axiom of choice,
So,
which is Z of C. The C stands for choice, right?
There was no
So Zorn's lemma is equivalent to, say, having a well-ordering of every set. Yeah, everything here. There are set of equivalences in set theory that I will not get to today. So just to summarize, what I wanted to show is two things. One of them is that discuss a little bit what can we learn about probability distributions, but the other is to show that the wonderful tools that are all equivalent for binary classification, they are not as smooth once we go to these tasks. And for all of those tasks that there was no dimension known before, we can now prove that there can be no dimension.
Okay, thanks, Shai. Sounds good. Oh, wait, we have one.
Shai, just a simple question. Did you say that you've also shown that there is no possibility of a dimension for real valued functions?
Right. No possible of scale invariant dimension.
Sorry, no?
No scale invariant dimension. Scale invariant dimension is I give you a dimension, and now for every
You mean something
delta,
outside of entropy numbers, for instance?
The entropy numbers are, for every epsilon, you have a different complexity of size epsilon.
Yeah, so that's what you mean by scale, right? Something like
Right.
that. Right. Yeah. Okay. Okay, that's fine. Thank you.
Okay, thanks, Shai.
Okay, thank you for listening. Bye.
Oh, and Shai, you're here in a month or two, right?
Yeah, I will be there for the workshop on domain adaptation.
Okay.
And yeah, hopefully I could visit more, but I'm teaching this term. Yeah.
Thanks.